A very good morning to one and all present here. I heartily welcome our beloved teachers and dear students to this seminar. Let's start this session with a prayer. I would like to call upon Saliha and Fatima to recite the prayer.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم اقرأ باسم ربك الذي خلق الإنسان من علق اقرأ وربك الأكرم الذي علم بالقلم علم الإنسان ما لم يعلم.
Translation. I seek refuge with Allah from the accursed shaitan. In the name of Allah, the most gracious, the most merciful. Surah Alaq, the plot. Recite in the name of your Lord who created man from a clinging substance. Recite, and your Lord is the most generous, who taught by the pen, taught man that which he knew not. Jazakallah.
Thank you, Saliha and Fatima. Now I invite Aisha Mubashara to deliver the welcome speech.
Respected Principal, Vice Principal, Resource Person, Head of the Department, faculty members, and all fellow students. Assalamu alaikum and very good morning to everyone present here. It's my pleasure to welcome you all to this two-day state-level webinar on Introduction to Abstract Mathematics. The webinar have been organized to enable the students to refresh their creative minds and to be equipped with the necessary basic concepts to understand underlying essence of theoretical study of mathematics. In this connection, I'm delighted to introduce our resource person, Mrs. M. Parveen Banu ma'am, to the gathering. She is an assistant professor and research supervisor in Mazharul Ulum College, Ambur. She is an alumni of our college. She has completed BSc Mathematics in Justice Bashir Ahmad Said College for Women, MSc Mathematics and MPhil in Mathematics in Ramanujam Institute for Advanced Study in Mathematics, University of Madras. She has qualified JRF NET in Mathematical Science under CSIR UGC. Currently, she is pursuing PhD at Tiruvallur University in Difference Equation. She is an examiner and research guide in Tiruvallur University. She was the coordinator of Red Ribbon Club and Blood Donor Club from the year 2020 to 2021. She had been a placement officer in CGPC from the year 2014 to 2017. She was a member in Khidmatun Nisa from the year 2017 to 2018. She had presented 2 international seminars and 1 national seminar on the topics rough set theory and mathematical applications, recent trend in mathematics, and advances in computational sciences and engineering. She has also published articles on the topics forward and backward difference equations in digital signal processing and effectiveness of the extended Kalman filter through difference equation. We are extremely happy to have you today, ma'am. Now, I invite Mrs. M. Parveen Banu, ma'am, for today's webinar on the topic Introduction to Abstract Mathematics. Over to you, ma'am.
Thank you. Thank you for such a wonderful welcome speech.
Parveen, be little louder, ma.
Assalamu alaikum wa rahmatullahi wa barakatuhu. Am I clear, ma'am, now? Is it okay?
Yes.
May peace and blessings of the Almighty Allah be showered upon all of us. First of all, I would like to thank Almighty Allah for giving me this opportunity to be a part of this event. So I would like to proudly introduce myself as an alumni of this institution. Also, I'd like to thank our principal, organizer, and the Department of Mathematics, HOD Sabira ma'am and Aziz ma'am, for remembering me and inviting me to deliver a talk. Thank you all. So let me share my screen.
can start, Mrs. Parveen. You can start your presentation. Assalamu
Yes,
alaikum.
ma'am.
I'm Fatima Azhar.
Thank you, ma'am. Is my screen visible to you all?
Yeah, it's visible.
Okay, so let me start. So actually, it's a very important and good idea to organize seminar on Introduction to Abstract Mathematics in the beginning of the academic year for our final year students, as the students from lower class till now, till the second year, would have been focused more on solving problems and evaluating results. Once they step into the final year, they come across much theory than calculation. Hence, the students feel the subject is dry and tough. And if the students understand the idea behind the theory, the theorems, the results, the subject would be more interesting for them. And it's my job today to get your interest, to get the students' interest in the subject. I hope and pray that I'll do justification to it. Now, as the topic of today's webinar is Introduction to Abstract Mathematics. What is an abstract mathematics? Abstract mathematics is different from other sciences. In laboratory science such as physics, chemistry, scientists perform experiments to discover new principles and verify theorems. Although mathematics is often motivated by physical experimentation and computer simulation, but it is made rigorous through the study of logical arguments. In studying abstract mathematics, we use the notion called axiomatic approach. We take a collection of objects and assume some rules about their structure. Axioms are nothing but rules, conditions. Using the axiom, we wish to derive other information about the collection by using logical argument. We require that the axiom should be consistent. That means the condition, the rule which we give should not contradict one another. And we want that there should not be more axioms also, because if you impose more rules or conditions, then the examples which we get will be a very few related to the mathematical structure. Okay, with this introduction, let's begin. Let's see the outline of today's session. So we shall quickly go through by beginning with the discussion of what and modern algebra is. Then we shall look into the history and development, then explore some fundamental concepts of modern algebra, then go through some of its application, then move on to linear algebra, and finally conclusion, and shall at the end I'll give you some reference books for study. First, what is a modern algebra? In algebra, which is a broad division of mathematics, modern algebra, also called as abstract algebra, is a study of algebraic structures. Algebraic structures include groups, rings, fields, modules, vector spaces, lattices, and algebra. Modern algebra is actually about patterns. We can see similar patterns. You can see one pattern repeating itself across mathematics and try to extract the essential element of that pattern and turn them into a definition. This process gives you groups, rings, vector space, etc. Based on the name, you might think that it is similar to the algebra course which you took in your lower classes, just a little more abstract. But if you open a book on modern algebra, you will be for quite a shock. It looks nothing like an algebra you know. So to help you understand the subject let's look into its history and development. Modern algebra was developed in the 19th century. Deriving the interest in solving equation initially focused on what is now called Galois theory and on construction issues. Actually, in the year 1800, some mathematicians, they know how to solve linear equation, as we also know how to solve linear equation. For example, an equation ax equal to b, ax plus b equal to 0. How will you solve this equation? Yes, anyone? The equation ax plus b equal to 0. Solving means getting the value for x. Anyone? It's a very simple equation. Ax plus b equal to 0. Anyone?
Equal to minus b by a, ma'am.
X equal to minus b by a. This is a very simple equation. So using the symbols of addition, we can get it. Then next comes the quadratic equation of degree 2, a square x plus bx plus c. Even for this also, to solving this also, we have derived some formulas solving the quadratic equation. Then for cubic also. And even for degree 4 also we can manage. But what about higher degree equation? That is x power 5 equation. So that is difficult to get the solution just by just calculation. So there comes the young teenager named Galois, Evarista Galois. He answered this question of solving the higher order equation, and to do so, he used a tool that he called a group. Around the time, Carl Friedrich, another mathematician, was busy making discoveries of his own. He ironed out a new technique called modular arithmetic, which helped him solving many problems in number theory. Modular arithmetic share many similarities with this group used by Galois. The year 1800 also saw a revolution in geometry, which we call now Euclidean geometry. That was by Euclid, the mathematician Euclid, dominated that theme with his book The Element. But mathematicians began to realize that there are other geometries beyond it. Hence, groups were found to be a useful tool in studying such geometries. And soon, groups became a very powerful tool that could be used in many different ways. Like this, the group theory was born. Soon, new abstract objects began to take shape, like rings, fields, vector space, etc. This didn't happen overnight. It took years of hard work to find right definition. Altogether, they find the subject called modern algebra. At first glance, modern algebra may not be seem very applicable. In the beginning, it's as it is an abstract subject, so it will not have a direct application to the world around us. But every year, a new uses of modern algebra are found, and not just in mathematics, physics, chemistry, computer science, and other discoveries also found how useful the modern algebra can be. By the end of 19th century, many of the problems were in some way related to the theory of algebraic structures. Then here, the mathematician George Peacock was the founder of axiomatic thinking. So like making a proper definition by giving the axioms. So axiomatic thinking and arithmetic of algebra was introduced by George Peacock. As in other parts of mathematics, concrete problems and examples have played important roles in the development of abstract algebra, also called as modern algebra. Through the end of 19th century, many of these problems were in some way related to the theory of algebraic equations. Major things you can see that solving a system of linear equations. So we have not just one equation. If you have a system of linear equation, then that solving those problems lead to linear algebra. Then attempting to find formulas for solution of general polynomial equation of higher degree results in the discovery of group, as we saw Galois, due to Galois. Then arithmetical investigation of quadratic and higher degree forms directly produce the notion of ring ideals. So all these things were helpful in solving the problems. Now let's explore some fundamental concepts in modern algebra. Modern algebra extract the familiar concept found in elementary algebra. So as we know some operation, elementary algebra, we have seen addition, subtraction, multiplication, division. All these are operators we have used till now. Then we know the role of 0 and 1. 0 and 1 play some important roles. Then how does the integers, properties of integers. So all these operations, what we know, that has been abstracted in a general setting. So here is the list of fundamental concepts in abstract algebra. So first is binary operation. Binary, the word binary itself, we can see that we need two objects, will operate something, and then we'll get a new object. The notion of addition is abstracted. The binary operation, how does it started? This the notion of addition is abstracted to give a binary operation. Generally, we use this notation asterisk or star, we say. The notion of binary operation is meaningless without the set on which the operation is defined. So for defining a binary operation, we need a set. So if you take two elements A and B, A star B, by that operating the binary operator, we'll get another element A star B. So if that element belongs to the set S, then we say it as this condition is called closure. So that is satisfies the closure property. So we have two elements A and B. If you operate as using a binary operation, we'll get another element. If that element belongs to the set S, then we can say that the binary operation is closed, or the condition is called closure. Now, example of binary operation is, we have, as we know, addition, subtraction, multiplication, division. All this can be thought as a binary operation when defined on different sets. As we can see that addition and multiplication of matrices we know. Then even you can add and multiply vectors, polynomials. So all these are example of a binary operation. Next is associativity. Associativity is also nothing new for you. The word associative you have heard. So where have you heard the word associative? In which condition, or where have you come across this word associative? Anyone?
In certain functions, ma'am.
Yes, in certain function, associative, in set, we have used associative law, right? Can anyone say the associative law for sets?
Yes, ma'am. A intersection B A intersection B intersection C equal to A intersection B intersection C, and
Yes,
for union
yes.
A
So we
union B
can group
union
the
C.
elements. So addition of integers has this property. As I said, in sets also we have come across this. So that is the grouping of numbers to the added does not affect the sum. That means if you can group anyway, if you have number, if you have to add number 2, 3, 4, you can add first 2 and 3, then the result can be added to 4, or you can add 3 and 4, then the result can be added to 2. So this grouping does not change. Grouping of numbers does not have any effect on the sum. That is the associativity. And this concept has been generalized used for this binary operation. In general, this becomes A star B. A star is any binary operator. A star B, then if you operate first for the elements A and B, then with C will give you the same answer. If you do the operator on B and C, then with A. This property is shared by most of the binary operation. We can see that we don't, every time we don't check the associativity, as it is for all the most of the binary operation, not all, but most of the binary operations satisfy this associativity. And for counter example, we can see that subtraction and division does not satisfy this associativity. Subtraction, can you give an example? The subtraction operator does not satisfy this associativity. Simply you can take the number 1, 2, 3. Can you quickly check it? Just can you check it whether subtraction is an associative? Does it satisfy the associative law? No. So you can simply take 3 elements, 1, 2, 3 itself you can take. So first 1 minus 2. What is 1 minus 2?
Minus 1.
Minus 1. Then if you then minus 3?
Minus 4.
Minus 4. That is one answer. Then 1 minus 2 minus 3. What is 2 minus 3?
Minus 1.
Then 1 minus of minus, that becomes 2. So they are not equal, isn't it? So subtraction. Similar, you can see division also. Division also does not satisfy the associativity law. Is this okay till this? Shall I proceed with the next?
Yes, ma'am.
Okay, next comes the identity element. So identity element, the number 0 and 1. So we have a very special property of 0 and 1. The numbers 0 and 1 are abstracted to give the notion of identity element for an operation. So 0 is the identity element. That means what do you mean by identity? Identity, you have heard identity function, isn't it? What do you mean by identity function? It is a function on the same set.
Both the domain and codomain will be same, ma'am.
Yes, both domain and codomain will be same, and along with that, the image of an element is the same. It does not change. Domain and codomain should be same, and f of x equal to x.
Yes, ma'am.
It is, the image is the same. That means it has no effect when you operate. So the same property 0 has. 0 is an additive identity. You can see that if you add 0 to any number, it will give you back the same number, isn't it? So 0 is an identity, additive identity. Same thing for 1. 1 for multiplication. 1 multiplied by any number will give you back the same number. So 0 and 1, this particular property of 0 and 1 has been abstracted to give the notion of identity element for an operation. So 0 can be take it as an additive element for addition, and 1 is the additive identity element for multiplication. And what is the property which we want? What is the condition we want? A is if you operate on an identity element, it should give you back the same element A. So for a general binary operator star, the identity element E, just a notation E, any element which satisfies this condition is called an identity element. In general, we'll give you the notation as E. The identity element E must satisfy A star E equal to E. Star in the sense the binary operator. So it can be addition, subtraction, or we'll do some more examples, we'll see. So A star E, that means if you operate A on the identity, it will give you back the same, or E operated on A will give you back the same. And you have one interesting property that once an identity exists, then it is unique. A binary operator cannot have two identities. Once if it exists, it will be unique. Okay, now same thing as this condition hold for addition, that is A plus 0 is A and 0 plus A equal to A, and multiplication is A multiplied by 1 is A and 1 multiplied by A is A. So this is the property of identity. Identity means if you operate it with other element, will give you back the same element. You can see that not all operator will have an identity element. So one example is here, the set of natural number. Natural number 1, 2, 3 has no identity element for addition, because 0 only satisfies those property and 0 does not belong to the natural number. Is it clear? This one counter example for an addition operator not being in the set. For addition, 0 only satisfies that property and 0 does not belong to the set, because the element should exist in the set. Okay, let's move next. Next is inverse. Inverse, the negative elements. How does we get the concept of inverse elements? Means the negative elements give rise to the concept of inverse elements. What does the negative element do? If you operate on 1, it will give you back the identity element. For addition, the inverse of a is minus a. If you operate a and minus a, will give you the 0 for additive identity. Multiplication, the inverse is a inverse. So the condition, this is the condition for an element to have an inverse. So a general two-sided inverse A inverse satisfy the property that A star A inverse equal to E. That means A inverse is the inverse of A. If you operate A and A star, A and A inverse will give you back the identity element. Same thing, A inverse star A is also, we should also give you the identity element. So we can check it for numbers 0 and 1. 0 and 1 is additive identity. So for any element A plus minus A will give you 0, where 0 is the additive identity. For multiplication, A multiplied by 1 by A. 1 by A is the multiplicative inverse. Next is commutative. Even commutativity, the word you would have come across. That means the order does not matter. Addition and multiplication are both commutative. That is, changing the order of numbers does not affect the result. That is, if you add 2 plus 3 or 3 plus 2, will give you the same answer. So that is, the order does not have an effect on the result. So in general, A star B equal to B star A. If this operator satisfies this condition, then we can say that the operator satisfied the commutative property. And we can also see that this property does not hold for all binary operation. So particular example is subtraction and multiplication. We know that 1 minus 2 is not equal to 2 minus 1, isn't it? Subtraction, we can't change the order. Is it okay?
Yes, ma'am.
So now, till now we have seen, what are the concepts we have seen? Binary operator, then?
Identity.
Yes, identity, element,
And
associativity.
Associative, ma'am.
Yes, then inverse and commutative.
Commutative.
So all this abstracted notion will group together, will combine those to form a new structure that we are going to look into the next. So a group. So a group is combining all the above concepts. It will give you the most important structure in mathematics, that is called a group. A group is a combination of a set, G we denote for group, and a single binary operation star, written as, we can write it as an ordered pair, because on set with the operator, so which satisfies the following properties. Any set with a binary operation satisfying the below 4 condition will give you as a group, will be called as a group. So if A and B are in G, the elements A star B. So if you operate, we'll get a new element, right? That element should belongs to the element G. So which we have seen is as a closure property. That means the binary operation which is defined will give you the new element in the group. So A comma B belongs to G. The defined element A star B should belongs to G. So if that satisfies, then the condition is called the closure condition. That is the first condition. Second is associativity. For any 3 elements A comma B comma C, A star B star C equal to A star B star C. All these things we have seen before, just we are collecting together. So first is the closure property, second is the associative property, then third is the identity element should exist. If in a set along with this operator, if there exists an identity element in G, that is very important. The identity element should belongs to the set. An identity element E exists in the set such that for every element A of G, E star A equal to A and A star E equal to E. That is the existence of identity in G. And the fourth is the inverse. For every element, we should have an inverse. So for every element, there should be there should exist an element A inverse which satisfies this inverse condition. That is A star A inverse equal to A star A inverse star A equal to E, where E is the identity element. So closure property, associative, existence of identity element, and existence of inverse. All these 4 conditions together along with the binary operation will give you the structure of a group. Is it okay? Group means you should have a non-empty set with a binary operation which satisfies these 4 conditions. First is the closure property, that is, given any 2 elements, the operated element, new element should belongs to the set. Then associativity, that means grouping will not have an effect. Identity element, there should exist an identity element which satisfies the identity condition. And for every element, we should have an inverse. So this together, all these four conditions together with the binary operation for a non-empty set give you a group structure. Next is abelian group. Abelian group means a group G with star. Already we should have a group. That means these four conditions should be satisfied. Along with this, if you have this additional condition of commutativity, A star B equal to B star A. That means all these four conditions will give you a group. Additional to this four condition, if the operator satisfy the commutative property, then we can call it as an abelian group. Now, can you give an example? That means you should give a set and an operator which satisfies all these four conditions. Can you make a try? Just known sets. You can take natural numbers, integers. What are unknown sets? Real numbers, anything. So you should give one set and an operator which satisfies all these four conditions. Simply you can try with addition. Addition we can try. So first basic set, what we know, natural numbers. Does natural numbers with addition satisfy all these four conditions?
Yes, ma'am.
All the four? First condition.
No, ma'am. It does
if you
not
add two numbers,
satisfy identity.
Yeah, this we have seen before, no? Identity element, natural number 0 does not belong to the natural number. So for addition, only 0 satisfies the identity condition. And so natural number does not form a group. So we have to check all the four conditions. It does not form a group under addition. Then we can extend the group. We need 0, right? Include that 0. If you include that 0, is it
number group, ma'am?
Yes. Whole numbers. If you include 0 along with the natural number, you have whole number 0, 1, 2, 3. Does it satisfy all the four conditions?
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
All the four? So as you know, natural number does not have an identity. So included 0, identity is okay. What about the inverse? Inverse, what is the inverse of 2? Additive inverse of 2. That means we know the identity element is 0. So what can be added to 2 to give 0?
Minus 2.
Minus 2. Does it belong to the whole number?
No, ma'am.
No. So even the set of whole numbers does not form a group under addition. So we have to
then set of integers in addition, ma'am.
That's good. So what is the lagging elements? Negative elements. So if you include that negative elements, so that is a group of integers that satisfies all the four conditions. So integers with the addition operator forms a group. Is it an abelian group? Is it an abelian group? Abelian means just along with this four condition, you have to check this. Does the addition operator satisfy commutativity? A plus B equal to B plus A.
It satisfies the commutativity, ma'am.
Yes, so it's an abelian group. So the set of integers along with the addition operation. So we can see the example. First is the set of integers under the operation of addition. So we can write it as Z plus. So you have to write the set along with the binary operator. So it's an abelian group. In this group, the identity element is 0 and the inverse of A is negation minus A. Is it okay? Now, next example is the set non-zero rational numbers. Rational numbers means what? How does the rational number looks like? What do you mean by rational number? Yes, fraction. M by n form. M and n are integers and denominator should not be 0. So the non-zero rational numbers, so along with the multiplication operator, forms an abelian group. Multiply identity is 1. So 1 belongs to the rational number and inverse is 1 by A. 1 by A also belongs to the rational number. Can you just tell me why do we exclude the 0? I have written Q minus 0. What happens if you include 0? Where does it, which condition fails? Why we are excluding 0? Rational along with multiplication is not a group. Only if you remove 0, it forms a group. So why do we want to remove the 0? What does 0 does not satisfy? Yes?
Zero.
Yes, someone said something. Can you repeat?
In fraction, the denominator is never 0.
The fraction, the denominator. So what inverse of 0 is 1 by A, right? So 0 does not have an inverse. So divided by 0 is infinity, which we have not defined. So we need to exclude this 0. Is it okay?
Yes, ma'am.
Okay. So rational numbers, non-zero rational numbers along with multiplication forms an abelian group, which one has an identity element and inverse is 1 by a. Okay. Next we can see some which is not a group, as we saw the integer under multiplication. So integer, already we have seen two examples, that is rational number along with addition is not a group. Even whole number does not form a group. And one more example for not a group is integer under multiplication. Why? Multiplication means inverse 1 by a. No fraction is not there in the integer. So it does not form a group because 4 is an integer, but its multiplicative inverse is 1 by 4, which does not belong to the integer set. Because if you know the counter example, not form a group, that means we have understood the concept clearly. Shall we move to the next? So next we shall see some properties of groups. Now we have a group G along with binary operator, means it satisfies all the closure, associative, then identity, then inverse property. So first thing is, this we have seen already, identity element, if it exists, is unique. If the identity element exists, then it is unique. Then for every A in G has an unique inverse. Even the inverse is also unique. Once you have an inverse for A, the inverse will be unique. And you can see that third property is, if you take one inverse, the inverse of A, then again inverse will give you back the A. This looks like an obvious property, but even for general abstract setting also this satisfies. A inverse, the whole inverse equal to A. All these things we can derive from the 4 condition itself. In the 4 conditions you can check all these properties. A inverse, the whole inverse equal to A. And the last property is A star B, the whole inverse equal to B star B inverse. There should be a star here. B inverse star A inverse. So this property usually called as socks and shoes property. So why is it called socks and shoe property is, so first when we wear shoes and socks, what do? First you will wear socks, then you'll wear the shoe. When you remove it, you'll do it in a reverse order. So only to note down that we have given this name. So socks and shoe property, that is AB, the whole inverse. First, if you do the operator A with B, if you reverse it, then it will be in the reverse direction. B inverse star with A inverse. So next comes the subgroup. Once you have a set, you have a subset. Subset means some collection. So a non-empty subset H of a group G. Already we have a group with a binary structure. So G with star binary operator, this satisfies the 4 condition. Then we are taking some subset of G, that is some collection of G, H, which we denote. A non-empty subset H of a group G with star is said to be a subgroup of G. When does it call H as a subgroup of G? Means if H itself forms a group. If under the operation star, same operator, if under the same operator, H itself forms a group. If H forms a group under star, that means H will not have all the elements. H is a collection of G, subcollection of G, you can say. H is a subcollection of G. If H with this same operator satisfies all the 4 conditions, then you can say that H is a subgroup of G. Is this subgroup definition clear? You have a subcollection. Already you have a group. G with star is a group. Take one subset H of G. Then this H is called a subgroup of G. If under the same operator, you can define some other operator and you can say it's a group, but it will not be called as a subgroup. Under the same operator, if it satisfies the 4 conditions, then you can say it as a subgroup of G. Now subgroup means same thing, we need to check the 4 conditions, right? But you can see there is a result that no need to check all the 4 conditions. These 2 conditions are enough. Once it satisfies these 2 conditions, the other 2 conditions follow. So that is called as a lemma. That's a result. A non-empty subset H of a group G with star is a subgroup of G if and only if A comma B belongs to H implies A star B belongs to H. That means it should be a closure property should satisfy. If you take 2 elements in H, if you operate the star operator, then the result should belongs to an element. Should be an element in H. And the second is, for every element A in H, A inverse exists in G, but the A inverse, if it belongs to the H set, then you can say it as a subgroup. So the 4 condition has been reduced to the 2 condition. Which are the 2 conditions left out? The definition says that H itself should form a group. That means H with its star operator should satisfy those 4 conditions. But we are telling that only these 2 conditions are enough. What are the conditions missing out? First is closure is there and inverse is there. What are the other 2 conditions which is missed out?
Associative.
Associative and yes, one is associative. Total 4 condition. No, we have written only
Commutative.
2. No, commutative is for abelian. That is a different structure. For being a group, we need 4 condition. One is closure, associative. What is the third one?
Identity, ma'am.
Yes, identity, then inverse. The 4 condition. So there is a result which says that no need to check all the 4 condition. Only these 2 conditions are enough. That is, it should have a closure property and it should have an inverse. Every element of H should have an inverse in H, and taking 2 element operating will give you an element in H. So the missed out property is associativity and identity. And you can see that associativity is clear. Once G is associative, H will also be associative. G with the star is associative means H with star will also be associative. Now only the identity element you have to check. Identity element you can check that if you have A in H, A star belongs to H, isn't it? Now you have 2 elements in H. What is A star, A inverse? G is a group, right? A and A inverse both belongs to G also. So what is A star, A inverse in G? A star A inverse should be equal to the identity element, no? So A star A inverse is equal to E, and you can see that any 2 elements in H, the operator belongs to the H. So A star A inverse will belongs to H. So E belongs to H. That is an obvious condition. Obvious means it is a consequence of these 2. These 2 conditions together will give you that identity belongs to the H. So that condition has been removed because on these 2 will give you that, and associativity follows because of G. So to prove any 2 condition, subset H to be a subgroup of G, we need to check only these 2 conditions. Okay, you have an example of a subgroup. Let G be a group of integers with addition. So it's a group. Let G is a group set of integers with addition. It forms a group. Now we are taking one subcollection H. It is a subset consisting of all multiples of 5. That means G is a group of integers means you'll have plus and minus 1, plus and minus 2, 0, etc. H is a subset consisting of multiples of 5. What is H set? Can you expand the set H? Yes, can you expand the set H? G is a group of integers under addition. We have a group of integers. So G is the set of integers. It's a group under addition. Now H is the subset of consisting of all multiples of 5. So
Yes,
can you
ma'am.
expand? Yes, can you expand the H set H?
5, 10,
Yes.
15, 20, it goes on.
Will 0 belongs to H?
Yes, ma'am.
No, ma'am.
Yes, 0 also belongs to H. So H is a subgroup because you can check these 2 conditions. If you take 2 elements, if you add it, if you take 2 multiples of 5, if you add, that will also be a multiple of 5, no? Just take 2 elements. Multiple of 5 means what? 5k you can take. So 5k1, 5k2, if you add 5 times k1 plus k2, that's still a multiple of 5. Then inverse, additive inverse. If 5k belongs to H, then minus 5k also belongs to H. So that is additive inverse. So these 2 conditions satisfy, so it's a subgroup. Now next is an important theorem in group, which is called a Lagrange theorem. So before looking into the theorem, so we need one more concept called order. So what is an order of a group? Order of a group is number of elements in the group. If you have, till now we have seen only infinite, because set of integers, set of rational, all that are infinite. So I'll give you one more example. Just check the set G equal to 1 comma minus 1. Yes, 1 comma minus 1 under multiplication. Just 2 elements, a set G 1 comma minus 1 under multiplication. Can you check whether it forms a group? Yes. a set G just with two elements, 1 comma minus 1 with multiplication. Because till now we have seen only infinite groups. One example of a finite group, 1 comma
Yes,
minus
ma'am.
1.
It forms a group, ma'am.
Does it form a group? Yes, only two elements you have. What is the multiplicative identity? 1. So inverse
Yes,
of
ma'am.
1 is 1 itself.
-1.
Multiplication.
Yes, ma'am.
Inverse of 1 is 1, inverse of minus 1 is minus 1. Under addition only you will have minus. But for addition, 0 is the identity. So I'm talking about multiplication. The set 1 comma minus 1 with multiplication. So it forms a group. So how many elements are there? Only two elements, no? So order of the group will be 2. So order of O of H we denote O of G, O of H. That means that give you that is nothing but equal to the number of elements in the group. So now we can see the statement. If G is a finite group and H is a subgroup of G, then order of H is a divisor of order of G. So this is one very important theorem in group theory. So if G is a finite group means number of elements in the set is finite. If G is a finite group, then H is a subgroup of G and H is a subgroup of G, then order of H is a divisor of order of G. And this Lagrange theorem has some two important application in proving the known classical theorem. So this Euler and Fermat's theorem, Euler's theorem and Fermat's theorem are the classical theorems in number theory. So these two theorems can easily be proved using this Lagrange theorem for some definite group structure. So Lagrange theorem has some two important application in proving the known classical theorem in number theory, named Euler and Fermat's theorem. Have you heard this Euler and Fermat's theorem in number theory? Maybe in your first semester you would have come across these two theorems. So these two theorems can be easily proved using the Lagrange's theorem. So Euler theorem is, if n is a positive integer and a is relatively prime to n, then a power phi of n. What is phi of n means? It is the number of integers relatively prime to n, less than or equal to n. So congruent to 1 mod n. And Fermat's theorem, it says that if p is a prime number and a is any integer, then a per p is congruent to a mod p. Okay. So next is homomorphism. So you can see that this is the common property which is shared by all the structure of modern algebra. If there is an idea which is common to all aspects of modern algebra, it is the notion of homomorphism. Homomorphism, this notion is shared by all the concepts of modern algebra. So by homomorphism, we means that a mapping, it's a mapping actually from one group structure to another algebraic structure. You can say, in general, we can say any algebraic structure. So which preserves the structure. That is, in particular for groups, we can see that you should have two groups, G1 with star and G2 with dot. Just to distinguish, we are putting star and dot. So you have two groups with two binary operator, let G1 star and G2 star be two groups. A homomorphism F from G1 to G2 is a mapping F from G1 to G2 such that F of A star B equal to F of A dot F of B. So just you have to understand this condition. What we are doing here is, first we are operating the element of G1, taking two element in G1, operating, then taking the image. That will give you the same result as first taking the image, then operating. Once you take the image, the elements belongs to G2. In G2, the operator is dot. Is this condition clear? What we are doing? First, we are taking two elements in G1. Then G1 operator is star, operating the binary operator of G1. Then taking the image. Will give you the same answer as first taking the image f of A, f of B. This f of A, f of B belongs to G2. In G2, the binary operator is star, then operating star. That both are equal. F of A star B equal to f of A dot f of B. This condition is called structure preserving condition. So intuitively, one should think about a homomorphism as a maps of sets which preserves the underlying group structure. So whatever the structure, whatever the binary operator we have, that should be preserved by the mapping. The mapping should preserve this underlying group structure. So if you have homomorphism, here we said two different groups, right? Suppose both the sets are equal. That means we have a same group G1, we denote it as G. So if a mapping is from G to G, if this satisfies this condition, they will call such mapping as endomorphism. If you have different groups, we call it as a homomorphism. If the underlying group is same, a homomorphism from group to itself is called an endomorphism. So there is one example for homomorphism. So we need two groups. One is R. R means set of all real numbers with addition. You can see that set of all real numbers with addition forms a group. And the second one is real numbers removing the non-negative, non-zero real numbers with multiplication. Because once you do multiplication, 0 should not be there because 0 does not have a multiplicative inverse. Once you have a multiplicative operator, you should remove 0. So non-zero real numbers along with multiplicative operator. This is another group. First group is real number with addition, non-zero real number with multiplication. Both the sets are groups. Now we are finding a mapping f from G1 to G2. How does it define? F of a equal to 2 power a. So in order to verify that the mapping f is homomorphism from G1 to G2, what we need to check, and what we have to check, we have to check this condition of homomorphism. So left side, the operator is addition, and right side, the operator is multiplication. That is f of a plus b equal to f of a dot f of b. So what is f of a plus b? It is 2 power a plus b. And that is equal to 2 power a into 2 power b. We know this property of powers, right? So what is 2 power m plus 1 n is 2 power m into 2 power n, no? So this property we have, and that is nothing but f of a and f of b. So f of a dot f of b. So which is indeed true. So f is a homomorphism from G1 to G2. So can you check that it's an homomorphism because of this property of power property? 2 power m plus n equal to 2 power m into 2 power n. This property we have already seen. We have already come across this. Because of this property, we can check that f is a homomorphism from G1 to G2. Is this okay? Can you all able to follow?
Yes, ma'am.
Okay, next is isomorphism. Isomorphism means it's a homomorphism. That means the mapping should preserve the structure, and along with that, if it is bijective, that means 1 to n and on to. A homomorphism f from G1 to G2, which is bijective, 1 to n and on to. It should preserve the structure. Along with preserving the structure, it should be a 1 to n and on to. Then it's called an isomorphism. So if two groups are said to be isomorphic, if there exists an isomorphism, we can say two groups are isomorphic to each other if you can find a mapping which preserves the structure and which is both 1 to n and on to. Then those two groups are called isomorphic. So intuitively, two groups being isomorphism means if two groups are isomorphism, that means both the groups are same, that both the groups have the same structure, only the labeling is different. So you can think if two groups are isomorphic, you can think it as a same group with relabeled elements. So next is an isomorphism. An isomorphism forms a group to itself. As we saw, homomorphism onto itself is called endomorphism. No, same thing. An isomorphism from a group to itself is called an automorphism. So one example of isomorphism you can see. So we have taken real numbers with addition and real numbers. Actually here only multiplication is there. Real r plus actually. So that means positive real numbers it is. So positive real numbers with addition and real numbers, positive real numbers with a multiplicative operator. Positive real numbers means no zero, no negative numbers. So positive real numbers with a multiplicative operator and real numbers with addition operator. These are the two sets. And how is the mapping defined? F of a equal to log a. You can check that this f is 1 to n on 2 and it also preserves the structure. Log of ab equal to log a plus log b. The two set, this is the positive real number. Positive real number means no zero, no negative numbers. We are removing the zero and the negative numbers. Only positive real numbers we are considering along with multiplicative operator. And the other group is set of real numbers with addition. So log function, log of ab. Why ab means first we have multiplicative operator. So log of ab. We know that log of ab equal to log a plus log b, which is same as f of a plus f of b. So it preserves the structure, and you can see that log is also 1 to n on 2. So it's an isomorphism from G1 to G2. Now you can see that till now we have come across only sets like addition, like integers, whole numbers, rational, reals. Now we are going to two another examples. One is congruence modulo n and the other is symmetric group, because these will be useful later. So it is not always you will have integers, real numbers will not have a very fine structure, no? So this is one of the example which is commonly used. So just try to understand this. Let n be a fixed in positive integer. So you have a n fixed positive integer in Z. We are defining a relation, congruence relation. So suffix n for the particular, because for this n integer we are defining. So congruence relation on the set of integers. How are we defining the relation is x is congruent to y if and only if n divides x minus y. So we can say x is congruent to y if and only if n divides x minus y. That is, x minus y can be written as nk for some k integer. Then you can quickly check that this congruence is an equivalence relation. So when does a relation called an equivalence relation? Yes, anyone? When does a relation called an equivalence relation? When is a relation said to be an equivalence relation?
When all the transverse, the three conditions are satisfied,
Yes,
ma'am.
good. Three conditions. What are they? One is
Symmetric.
transitive. That's right.
Reflexive,
Yes.
transitive,
and reflective, ma'am.
So reflective, symmetric, and transitive.
Yes, ma'am.
So you can check this relation, congruence relation, which is nothing but n divides x minus y, or you can use this also, x minus y equal to nk. That means x minus y should be a multiple of k. This relation satisfies all the three, reflexive, symmetric, and transitive. So it's an equivalence relation. Once you have an equivalence relation, it divides the set into, it partitions the set into equivalence classes. The equivalence classes of Z under this relation are indexed by possible remainder modulo n. So hence there are n distinct. So if you divide a number by n, so what are the possible remainders you can have? Suppose if you divide any number by 5, what are the possible remainders? What are the remainders you can have? Any number x, if you divide it by 5, what are the reminders I'm asking? When you divide, you will get a reminder, no? What are the possible reminders we can have? Yes, possible reminders when divided by
Other
5.
0 and 5, ma'am. 1, 2, 9.
Divided by 5. You are dividing any number, take any number, divided by 5. What are the possible reminders?
0, ma'am.
Yes, 0 can be, because once it divides, fully divide, you will get 0 as a reminder. Then not always 0, no? Every number will not be a divisor, will be divisible by 5.
Yes, ma'am.
Yes. So what are the other reminders, other possible reminders I'm asking?
1, 2, 3, 6,
Yes.
4.
1, 2, 3, 4 is okay. Will you get 6 as a reminder?
No, ma'am. No, ma'am. 1,
No,
When
ma'am.
divided by 5,
0, 1,
that
2,
is
3.
important. Yes. Will you get 6 as a reminder?
No, ma'am. 5
No.
No,
numbers, ma'am.
ma'am.
0, 1, 2, 3,
Will you
4.
get 5 also?
No, ma'am.
No, because it is divisible, no? 5 you will
Yes,
not
ma'am.
get, more than 5 also you will not. So the possible reminders are 0 you can have once it is fully divided, or 1, 2, 3, and 4. Isn't it?
Yes, ma'am.
So that is only our set of congruence. So we denote the set of all residue classes, we say, remainder classes, you can say. So residue classes, so will denote that set by Zn. Z is not the set now. Z is the set of all integers. If you take this relation, then the equivalence relation will partition the Z into equivalence classes. We denote that set as Zn, or you can take it as Z by, it should be N only, Nz, not Mz. N. We are not using M here. So Zn or Z by Nz. So Zn is nothing but the remainder, residue classes of reminders. That means 0 can be a reminder, 1, 2, if N, it stops till N minus 1. Isn't it? That is, for example, if you have Z5 means it will be a class 0, then class 1, class 2, class 3, and class 4 only you'll have. Only 5 elements will be there starting from 0 to 1. That means 0 will have all the numbers divisible by 5. 0 is not one single number. You take it as one element in Zn, but it is a set actually. It has all the elements, it has all the integers which is divisible by n. Then 1 means all the numbers when divisible by 1 give a reminder. For example, we can take Z5 itself, because you should understand this set very clearly. So this will be using very often in your later subject. So Zn equal to take Z phi, n equal to 5 you can take. For example, take n equal to 5. So you have classes 0, 1, 2, 3 and 4, isn't it? So class 0 is one element in Zn, but it is actually a set. So what are the elements which belongs to 0? All divisible by 5. All the numbers divisible 5. That means 0 will be there, 5, 10, 15, 20, 25, 30. Can you able to follow? The numbers which are divisible by 5 will belongs to the set 0, will belongs to the class 0. Can you say one element which belongs to the class 1? If any element belongs to this class, means it when divided by 5 should give you the remainder 1. What is the number when divided by 5 gives you remainder 1?
11,
Yes, 11.
21,
6 you have.
31.
Yes, 6, 11, then 16. Isn't it? All these
Yes,
numbers
ma'am.
which when divided by 5 give you the remainder 1. So if the remainder when divided by 5, if the remainder is 0, it belongs to the class 0. If the remainder is 1, the number belongs to the class 1. Can you say for 2?
Yes, ma'am. 7.
12, 17, 22.
Yes, 7, then 12, 17. That's good. So now did you understood this set? Is this set clear? Zn set?
Yes, ma'am.
Okay. Now you have an exercise here. Now consider Z10. That means you have to divide the number by 10. So totally how many? You'll have 10 elements in the class, no? Zn will have 10 elements. 0, 1, 2, 3 up to 9 you'll have. So now here some of the classes are equal. So can you say which of the classes are equal? That means, see, you have, I said 0 class. What are the elements belongs to 0 in Z5? 0, 5, 10, 15, isn't it?
Yes, ma'am.
So 0
Yes,
class is
ma'am.
same as 5 class. If you write 5 also, 0 is only a representator. You can change the
Yes, ma'am.
representator also. So 0 class is same as class 5 also.
Yes,
Then
ma'am.
it is same as
Here.
class 15. It is same as class 10, isn't it? 0 is just a reference. Among that elements, you can take one element and you can say it as a class. Now, same here. Can you classify the classes here? Which are equal? Which of the classes are equal here? It is in Z10. Remember, your base is 10. Yes, which are the classes here are equal? Which gives you the same reminder. You have to check that. See, for example, 12. 12 when divided by, so can you see class 2 and class 12 are same? Yes. Can you see class 2 and class 12 are same?
Yes,
Will both have
ma'am.
a same element. When divided by 10 will give you the remainder 2, isn't it? 2, the class 2 includes the number 12. If you have same element, the two classes are same. The class 2 will have 12 elements, so 2 and 12 class are same. 22 is also same. 2, 12 and 22 are same. Yes. Minus 5, 5, 15 are same. Okay, so you can go through this again, then you can try to answer. Is this, at least this is fine? Is 2 and 12 class, 22 class are same? 2, 12 and 22. See, 2 in the set 2 you'll have 12. If you have two elements common, then the two classes are also common. If you have a common element, then the whole class itself is same. Okay, next under the Zn, we can define the addition operation. So addition modulo n we can say. So on define this addition modulo n on Zn as the class AB. If you add, you will get the class A plus B. So you can check that this addition operator satisfy all the four conditions along with the commutative condition. So Zn with Z addition is an abelian group. So you can check that. So it is same as normal addition only. It's not a big deal. So normal addition you can think. Only thing is you have to see that two classes are equal if there is a common element. So next is a permutation group. So permutation group. So let S be a non-empty set. Permutation. This is another example which is very useful in group theory. So let S be a non-empty set. A of S. A of S is the set of all one-to-one functions from S onto. That means it should be one-to-one function and onto function. We can see that E of S equal to set F from S to S. So F is one-to-one function of S onto S. That means it's a one-to-one and onto function, but it's a bijective function actually. So you can take it as a F is a bijective function on S. So all bijective functions from S to S take the collection. This collection along with the composition of function. Once you have two functions, you can composite two functions and you get a new function. So this is the binary operator here, composition of function. This is a non-abelian group. You can see that if you have two functions, F composite G is not always same as G composite F. So it's a non-abelian group called a permutation group. Is this okay? E of S with composition. E of S consists of all bijective functions on S along with this composite operator. So it forms a non-abelian group, and this group is called a permutation group. And this is very important because it classifies the group theory. So that is given in the next theorem, Cayley theorem. So which is very important. This theorem classifies all the groups. Every group is isomorphic to a subgroup of E of S for appropriate S. That means any group if you take so it look like an A of S for appropriate S. It is isomorphic to a subgroup of E of, not all of A of S. It is isomorphic to a subgroup of E of S for an appropriate S. So this theorem classifies all the group theory. That means any group. If you define any group structure, that will be isomorphic to a subgroup of E of S for an appropriate S. You have to change the S accordingly. That means every group has this structure. It is a subgroup of E of S. So now once we are ended with the group theory, next is ring and fields. So you can see that in group theory we have only one binary operator. Group just have one binary operation to fully explain the behavior of the different types of numbers. That means you can see that in real numbers itself we have two operator. Addition also there, multiplication is also there. So to read the structure or numbers with two operators needed to be studied. The most important of these are rings and fields. That means here you will have in one set we'll be defining two operator. A ring has two binary operation, plus and dot. This is only notation, plus and dot. It can be any notation, star and dot you can say. So usually we don't denote as plus and dot, standard notation. With star distributive over addition. With dot distributive over addition. Under the first operator, it forms an abelian group. Under the second operator, it is only associative. That means closure will be there and associative. It need not have an identity and inverse. You have two operator. With first operator addition, it should be a fully abelian group. With respect to dot, only associativity and closure is enough. And because binary operator itself will include the closure property. So we have not mentioned here. So it's associative plus closure property also satisfied for dot. But dot need not have an identity and inverse. But it should have an additional condition called distributivity, which is in the next slide. So dot is distributive over F, means A plus B dot C equal to A dot C plus B dot C. The C dot A plus B equal to C dot A plus C dot B. This is the distributivity of dot over plus addition. So the example of a ring is set of integers with addition and multiplication. Because we have seen that with multiplication, it does not have a inverse, right? 1 by integers does not have fraction. But we don't need that inverse itself. So it forms a ring. Is it okay? Integers with multiplicative is not a group because it does not have an inverse. But for ring, for the second operator, we don't need inverse. So Z with addition and this multiplication is an example of a ring. Is this ring structure okay? In ring, we have two binary operator. One is addition and the other is multiplication. With addition, it should form a fully abelian group. That means closure, associative, existence of identity, inverse, and commutativity. But with dot, we need only closure and associative. Need not have identity and inverse. So we have an example as the set of integers. it should satisfy this distributive property which integers do with addition and multiplication. Next is field. So field is also some additional property along with ring. A field is a ring with additional property that all the elements excluding 0 forms an abelian group under multiplication. That means excluding 0, every number should form an abelian group. That means identity, the multiplicative identity should be there, and removing the 0, that was additive identity. If you remove the additive identity, then it should form a abelian group under this dot operation also. So multiplicative identity should be there, which is denoted as 1, and multiplicative inverse for A is A inverse, not for 0. So example is all rational numbers, real numbers, complex numbers are all examples, standard examples of fields. We don't have to remove 0 because already 0, we have, in condition itself we have removed 0. So other than 0, we should have an inverse. So rational number, even 0 you can include in the field structure. So with this abstract algebra, the modern algebra, we have seen group structure, field structure, ring structure. So now we'll look into some applications of modern algebra. So the branch of mathematics which studies real world application, you can see that all real world application, it comes under, we say that only applied mathematics and computational mathematics has application. But this applied mathematics and computational mathematics has a strong foundation in modern algebra. The fact is that applied and computational mathematics is built on foundations led by abstract algebra or modern algebra. So we can't say that modern algebra does not have a real life application. So real world application directly applied to applied and computational mathematics, but these two itself need a foundation of modern algebra. So the extended theory is algebraic topology, algebraic number theory, physics. In physics, you can see that the group structure is used in the terms of symmetry. To finding symmetry in the structure, we need group theory or the abstract algebra. Then functional programming, coding theory, we can see that error coding, we have to write a program, error coding, correcting codes are used in almost all forms of satellite communication. But to write this error coding, this abstract algebra or modern algebra plays important role. So next is what is a linear algebra. So sometimes linear algebra is also called one branch of modern algebra. So linear algebra is a branch of mathematics that studies vector spaces, also called linear spaces, along with linear functions that input one vector and output another vector. So it's called a linear function, study of linear functions actually. So it has extensive application in engineering, physics, natural science, computer science, and social science, so particularly in economics. Non-linear mathematical models can often be approximated by linear ones. So the study of linear algebra and matrices has a long history. So it was emerged from determinants. We have matrices, determinants. From there, this linear algebra has been evolved to solve the system of linear equation, where we used to solve system of linear equation. Determinants were used by Leibniz in 1693 and subsequently by Kramer 1750 to solving linear equation. So in linear algebra, we have a structure like extension of group, ring, field. So you have a structure called, this is also an abstract structure, so vector space. So the difference between the previous structure and this is, here also you have two operators, addition and multiplication. We call it as a scalar multiplication. There we have seen that in field and ring we have two operators. Both the operator belongs to the same set. But here we have another set to be included. A non-empty set V is said to be a vector space. It is also called as linear space over a field F. If V is an abelian group under addition, you have two operators. First is addition. So V should be an abelian group under addition. And you have another operator called scalar multiplication, we say. The beauty of the scalar multiplication is we take one element from the field and the other element from V. So we are taking alpha belongs to F and V belongs to V. Then the resulting element should belongs to V. There is defined an element written as alpha V. This alpha V should belongs to V. So this you should note down, because in rings and field also you have two operators and both the operator will define on the same set. But in vector space, with first operator addition is fully defined on V and it is a group, abelian group under addition. But with the second operator called a scalar multiplication, that means we are multiplying with a scalar. Elements of field are called scalars and elements of V are called, vector space are called vectors. So we call it as a scalar multiplication. That means we are multiplying a scalar with the vector alpha and v, and the result is a vector. We are taking one element from F and other element from V, scalar from field and vector from V. If you combine, you will get a new element, and that element belongs to V. And it should satisfy this condition, the scalar multiplication. Alpha of V plus W is alpha V plus alpha W, that is, it is distributive. Alpha plus beta into V equal to alpha V plus beta V. Because in field itself we have addition. This addition belongs to the field addition. Then alpha of beta V equal to alpha beta of V. Then 1 and 1 into V equal to V. This 1 is the unit element of field. Unit element of field, 1 has the property, but not with V vectors, right? So this is an additional condition. So you should not take it as an obvious, because 1 is the multiplicative identity of field. So we are multiplicative identity of field with vectors also satisfy the same condition. 1 with V equal to V. So this is the definition of a vector space. So you should note down one point is here you have two sets. One is V, the other is F. V is called elements of V are vectors, elements of F are scalars. So you have two examples. So let F be any field. If you take any field, if you write the Fv equal to f of x, the set of polynomials in x over F, then this f of x is a vector space over F. And you have another example. This is very important because this will be using very often in later in the slides also, and in your course also. Let F be any field. Take any field, that means you have scalars. V equal to Fn, that means n copies of F. V is a new set in the sense all the elements belongs to F only. So try to understand this example very clearly, because this will be using often in your course. So let F be any field, V equal to Fn. That means it is just n copies of F. So one element you can write it as an ordered pair, alpha 1, alpha 2, alpha 3 up to alpha n. So this ordered n triple is a vector, but you can see that all the elements are scalars only. Alpha 1, alpha 2, etc. alpha n, where alpha is belongs to F. So take two elements, because if you have to define a vector space, you have to define two operators. One is addition and scalar multiplication. So take two elements, alpha 1, alpha 2, alpha n, and beta 1, beta 2, beta n. So you can say that these two elements are equal if each pair is equal. That means alpha 1 is equal to beta 1, alpha 2 is equal to beta 2, like this alpha n. So two elements are equal, two ordered tuple are equal if each pair is equal, each ordered element is equal. So now define addition and multiplication like this. Addition of two elements, alpha 1, alpha 2, etc. alpha n equal to. So you have to order wise addition, alpha 1 with beta 1, alpha 2 with beta 2, alpha n with beta n. This is the addition defined. And scalar multiplication is gamma is a scalar into this vector, gamma into alpha 1, alpha 2, alpha n is gamma 1, alpha 1, gamma 2, alpha 2, etc. gamma n, alpha n, where gamma is a scalar. So you can easily verify that with this addition and scalar multiplication, this V, which is same as Fn, forms a vector space. So next is linear transformation. So you can see that linear transformation. So the importance of vector space or the linear algebra lies in the concept which we are going to look into next, that is linear combination, linear transformation. You have linear span, basis, all that things. So linear transformation, basis, all these are important facts that so many models arising in the solution of specific problems turned out to be a vector space, in vector space. So the fundamental concepts we are going to see, first is linear combination. So linear transformation. Linear transformation is nothing but, we have seen homomorphism in the group theory, it is like the same thing only. So here, because of linear space, we use the word linear transformation. It is nothing but a mapping which preserves the structure. That means you have two structure here. One is addition and scalar multiplication. So T of U1 plus U2 equal to T of U1 plus T of U2. Then T of alpha U1 equal to alpha T of U1. So same thing, it should be a mapping from one vector space to another with a structure preserving. So it is same condition as homomorphism. We call it as a transformation mapping. Is said to be homomorphism if it preserve the structure. That is, it should preserve the addition structure and preserve the scalar multiplication structure. So these two conditions can be combined like this. T of alpha U1 plus beta U2 equal to alpha times T of U1 plus beta times T of U2. Usually we use this condition. We don't find separately these two things. first addition, scalar multiplication, both can be combined. So most of the problems to check the linear transformation, we use this combined condition. So next is linear combination. Linear combination means the scalar combination only. So we have a vector space. V is a vector space over F. Then V1, V2, etc. up to Vn are vectors. Then this combination alpha 1 V1, that is scalar multiplication, then addition also. Alpha 1 V1 plus alpha 2 V2, etc. alpha n Vn. So where alpha is F as scalars is a linear combination over F. So next is linear span. Linear span means if S is a non-empty subset of a vector space V. So take one non-empty subset of a vector space V. V is a vector space. Take one non-empty subset. L of S is the notation for linear span. It is nothing but all linear combination of finite sets of elements of S. S is any set. Take some finite collection of S. Take a linear combination. So all the collection together forms a new set called L of S. You can see that L of S is a subspace of V. Then finite dimensional. So when do we say a vector space is of finite dimension? When if you find a finite subset S such that V equal to L of S. That means you have to find a finite subset of V whose span is same as V equal to L of S. L of S is nothing but the linear span of S. If you could find a finite set S whose span is equal to V, then we can say that V is a finite dimensional space. So you can see that this Fn is a finite dimensional. And what is the set S is these vectors 1, 1, 0, 0, 0, then 0, 1, 0, 0, 0, 1. You can see that this collection of vectors is finite actually because there are n vectors. So this is a finite collection, and you can see that linear combination of all these vectors will give you back the n. Any linear combination, just linear combination of these will give you the whole Fn. So you have a finite set whose span is Fn. So it's a finite dimensional vector space. So next is important concept is linear independent and dependent. So this you have to understand very well. So when you say that a linear combination is linearly independent. So if V is a vector space, you have a vector space over F. If V1, V2, etc., Vn belongs to V. Take some vectors, n vectors in V. We say that these n vectors are linearly dependent. When do we say that these n vectors are linearly dependent? If there exist scalars alpha 1, alpha 2 in F, not all of them such that alpha 1 V1 plus alpha 2. Alphas are missing here. So if there exists scalar, these are scalars alpha 1, alpha 2, alpha n. So, they are scalars in F such that not all of them are 0. Alpha 1 V1 plus alpha 2 V2, etc. alpha n Vn. So that means this set of vectors is said to be linearly dependent if you could find a set of scalars such that the linear scalar should not all be 0. With some non-zero scalars, if you find this combination equal to 0 should be there. So if V1, V2, etc., Vn are not linearly dependent, suppose this collection is not linearly dependent, then we can say that it's linearly independent. So in the definition, 2 points are missing. One is equal to 0 and the other are alphas. Alphas are missing here. Okay, so now you can quickly go through an example. So they consider F3. Just to make it simple, I have taken only F3. F3, we have taken 3 vectors. One is 1, 0, 0, the other is 0, 1, 0, the other is 0, 0, 1. 3 vectors. We have to check that these 3 vectors are linearly independent. So when do we say that set collection is linearly independent? If it is not dependent. If it is not dependent in the sense, you have to find scalars. Check this. It's linearly independent if for scalars alpha 1, alpha 2, alpha 3, suppose you consider this alpha 1 V1 plus alpha 2 V2 plus alpha 3 V2 is equal to 0. You have to prove alpha 1, alpha 2, alpha 3. All these 3 are 0. All the scalars should be 0. If there is one non-zero scalar, then this collection is linearly dependent. Is it okay? The linear combination is 0. If the one of the scalar is non-zero, it is linearly dependent. If all the scalars are 0, then the collection is linearly independent. So you can see that alpha 1 into V1. Alpha 1 into V1 is what? Alpha 1, 0, 0. Alpha 2 into V2 is 0, alpha 2, 0. Alpha 3 into V3 is 0, 0, alpha 3. If you add, you will get alpha 1, alpha 2, alpha 3. And 0 vector means 0, 0, 0 vector. So equating will get alpha 1 as 0, alpha 2 as 0, alpha 3 as 0. So this collection is linearly independent, because if you have a linear combination, then all the scalars are equal to 0. So hence proving V1, V2, V3 is linearly independent. Now, can you quickly check this is linearly dependent? That means you have to find some scalars. Check this, try this out. Tell me 3 scalars, that means 3 numbers. When you multiply this V1, V2, V3, will give you 0. Can you quickly give 3 scalars, non-zero scalars? Give me 3, tell me 3 numbers. When you multiply it with this vector V1, V2, V3, will give you the idea, and if you add it, you should get 0. Yes, girls, can you try this out? You need to check these 3 vectors are linearly dependent. That means give me 3 numbers. When you multiply by V1, then V2 and V3 and add it, should get 0. Can you try that? 3 scalars you have to give. When you scalar multiply with these vectors and add it, it should get 0. You have 1 here. First take the first order you can take. First element 1, 3 and 5. You have 1, 3 and 5. What is the number which you multiplied by 1, then the number which you multiplied by 3, then 5 will give you 0. Can you try? Are you listening? Can you able to follow? Can you give me 3 scalars? Yes, girls, are you there? Yes, can you hear me?
Yes, ma'am.
Yes, can you tell me 3 scalars when multiplied by V1, then another scalar multiplied by V2, another scalar multiplied by V3, and if you add it, should give you 0. Just take first 3 numbers, 1, 3 and 5 you have. Yes. So you can take alpha 1 as 2. 2 into 1 is? Take alpha 1 as 2. What can be alpha 2? I have given one number. Can you try the other 2? Alpha 1 is 2. Alpha 2 will be 1. Okay, I'll give you 2. So alpha 1 is 2 and alpha 2 is 1. What can be alpha 3? Two numbers I have given, 2 and 1. So if you multiply this with 2, what you will get? 2, 2, 0. If you multiply this by 1, you will get same, 3, 1, 3. So you have 2, 2, 0 and 3, 1, 3. What is the number which you multiplied will give you 0? Multiply alpha 3, then add it all. Can you take it as a minus 1? Alpha 3 is minus 1. Alpha 1 is 2. Alpha 1 is 2. So 2, 2, 0. Alpha 2 is 1. Same 3, 1, 3. And if you take it as minus here, minus 5, minus 3, minus 3. If you add, you will get 0, 0, 0. Isn't it? So you are able to find some scalars, non-zero scalars you can find. So as you can find non-zero scalars, so this collection is linearly dependent. So, but you can't find non-zero scalars for this collection, V1, V2, V3. If for any collection, you will find ultimately, you will get alpha 1 is 0, alpha 2 is 0, alpha 3 is 0. So this collection is linearly independent, and this is one example for linearly dependent. Okay. So now next is important concept is basis. So a basis S of a vector space V is said to form a basis. A subset S of a vector space V is said to form a basis if it consists of linearly independent elements. That is, a finite elements of S are linearly independent, and V equal to L of S. S need not be finite, but of every finite collection of S should be linearly independent, and V equal to L of S. That means the spanning of S should give you V. If V is a finite dimensional vector space, then any two bases of V have the same number of elements. Suppose if V is finite dimension, that means you can find a finite collection S which spans, and that is linearly independent also. So any two bases will have a same number of elements. You can find two different bases, but the number of elements will be equal. So as the number of elements are equal, we are given that as new name called the dimension. So the dimension of V over F is the number of elements in any basis of V over F. So now this is the important result. If V is a finite dimensional vector space, any finite dimensional vector space is isomorphic to Fn. So any two finite dimensional vector space over F is isomorphic to Fn. So if you have a vector space of dimension n, then it is ultimately isomorphic to Fn. That means it looks like Fn. You can you can find a one-to-one bijective map from V to Fn which satisfies the structure. So next is any two finite dimensional vector space of same dimension are isomorphic. So next is inner product space. This is another structure on vector space. So let V be a vector space over F. So here from here on you can see F we can take R or C only, no other field. So our field can be real number or complex number. Then only we can define an inner product. So it is a function from two elements u comma v denoted by this inner product bracket. So the result is a scalar. That means it's a real number or complex number. So inner product of u comma v equal to inner product of v comma u, the whole bar in the sense conjugate. For real numbers it is the same. For complex you know the conjugate, right? Alpha plus I beta means alpha minus I beta, the conjugate. So and you can see that inner product is a positive and u comma u equal to 0. Inner product of two elements is 0 if and only if u equal to 0, and you have this linear condition. It's linear in the first variable we say. So alpha u plus beta v comma w equal to alpha into u comma w plus beta into v comma w. So one example here is in Fn. You can take this as a vector space. How we are defining the inner product is inner product u comma v is u is an ordered tuple and v is an ordered n tuple. So alpha 1 beta 1 bar plus alpha 2 beta 2 bar etc. alpha n beta n bar. So you can check that this definition satisfy all these above conditions. So it's a inner product space. So once it's an inner product space, you can define a norm. Norm is nothing but we can say it is the length of a vector also we can say. So length of a vector, the definition is root of inner product v comma v. And this norm notation and this inner product will give rise to a very famous inequality called Cauchy-Schwarz inequality. So if u comma v belongs to v, modulus of inner product u comma v is less than or equal to norm u into norm v. This inequality will be using often in many other proofs, many higher proofs, or in probability you can use this. So this inequality is used in various fields and this comes from the vector space. So next is orthogonal and orthonormal. So we can see that once you have length, all the things, length of a vector, we can see perpendicularity. The concept of perpendicularity is an extremely useful and important one in geometry. In geometry, we talk more about perpendicularity. We need this condition. So that has been introduced using this inner product. Two vectors are said to be orthogonal if inner product is 0. You can see that if u is orthogonal to v, then v is orthogonal to u because of the first property. And then if you have a collection of vectors, this collection is called orthonormal set. When do we say a collection of vectors is orthonormal? If you can say mutually perpendicular, you can say that is any two vectors, they are orthogonal to each other. So for I not equal to j, vi comma vj equal to 0. That means vi is orthogonal to vj and each vi is of length 1. So if the length of each vector is 1 and every other vector is mutually orthogonal, you can say, or mutually perpendicular, you can say, any two elements if you take, the inner product is 0 and length is 1. These two conditions combined will give you this set as orthonormal set. And you can see that every finite dimensional vector space has a orthonormal set of bases. This is very important theorem. So there is a process called Gram-Schmidt orthogonalization process, because by the process you can construct an orthonormal basis for every finite dimensional vector space. So next we'll look into the application of linear algebra. So linear algebra is one of the most applicable areas of mathematics. It is used by pure mathematician and even mathematically trained scientists. Even in computer science we used matrices well, no? So mathematically trained scientists of all disciplines so use this linear algebra in artificial intelligence, machine learning, data analysis, even in economics, vector graphics, image compression. Even in game theory, we use linear algebra. So finally, we have come to the conclusion. So one of the amazing feature of 20th century mathematics has been its recognition of the power of abstract approach. So this is the amazing feature which have come across in 20th century. That is, we have come from the concrete to abstract approach. This has given rise to a large body of new results and problems, and has in fact led us to open whole new areas of mathematics, whose very existence have not been suspected even. In the wake of this development has come not only a few mathematics, but a fresh look, and along with this, simple new proofs of difficult classical results. We have seen that Euler and Fermat, that is a classical result in number theory, that can be proved easily using the group theory, Lagrange's theorem. The algebra, which has evolved as an outgrowth of all, this is not only a subject with independent type. This abstract algebra is not, this modern algebra is not fixed to one particular. So it has grown into another current important research also. So it is one of the important current research area in mathematics, but also serve as a unifying thread which interlaces almost all mathematics. So this developed all mathematics, geometry, number theory, analysis, topology, and even applied mathematics. So now these are some reference books for study. So first book, Ian Hurstian Topics in Algebra. This is your prescribed book for your course, both for modern algebra and linear algebra. Then you can go through this book also, Joseph Gallian, Contemporary Abstract Algebra. Then Dummit and Foote, Abstract Algebra by Dummit and Foote. This is also a very good book. And for linear algebra, you can go through this book, Stephen, Feuerbach, Insel, and Spence. These are the three authors. The topic is linear algebra. This book is also very useful in learning, in understanding the linear algebra. So hence I request our students to try to understand the concept when you begin the course. So in the beginning itself, don't let down. So try to understand the lectures from the beginning and try to understand the concept. In the beginning, it will be difficult. Surely in the beginning, you'll feel it as a difficult, but read it again and again. After every reading, you'll gain more understanding. The linear and modern algebra course is the basic of all higher mathematics. So wherever you go into the higher mathematics, this led as a foundation. This is a foundation for that. So this will lead to your research on any topic also. So with this, I conclude my presentation, and I once again thank the organizer and Department of Mathematics. Thank you.
Thank you, ma'am. The session was really interesting and helpful for us. Now, I would like to call upon Anisha Syed to deliver the vote of thanks.
Assalamu alaikum and good morning, everyone. I consider a great privilege to propose a vote of thanks to all the dignitaries present in the webinar. I begin by thanking the Almighty for making the first day of the webinar a great success. We never know that there are so much in algebra before this session, ma'am. Thank you so much, ma'am, for making the concept of linear and modern algebra much easier and interesting. I, on behalf of the Department of Mathematics and the students, personally thank the beloved speaker of the day, Mrs. M. Parveen Banu, ma'am, for her valuable information on linear and modern algebra. Thank you, ma'am. Last but not the least, I thank all the participants and volunteers for your active participation and full cooperation.